Okay, I decided to add another podcast here in terms of climate context, especially because we also want to know how biodiversity, vegetation would have evolved. We looked at a little bit about megafauna and so on. So this is another nice collection of figures we can use to make a little bit more point about how climate and vegetation biodiversity over East Africa has varied over the last 10 to 15 million years, especially during the evolution of hominins, bipedalism, East African aridification that we mentioned in terms of the change in the Pacific, going from presumably a permanent El Nino to what exists now as an episodic El Nino, which happens every 2 to 7 years. I have lots of podcasts on El Nino related topics that you can look up. So let's start with this one from an NRC book on climate impacts on human evolution. We are looking at 8 millions to about the present. The scale is very coarse, so you have to be careful. And we are looking at possible and probable early hominins, and these evidences keep shifting. As I said, more and more new evidences may emerge along the way, and of course there were other great apes as well. And archaic hominins arrive here around between 4 and 5 million years, especially Australopithecus aramensis that we have looked at, Remidus, and so on. Megadont archaic hominins here, Paranthropus, transition hominins, so we went from Australopiths and Paranthropus who may have coexisted with the Homo lineages. So here we have Homo species evolving around 3 million years ago, Homo rhodophensis, habilis, erectus, and then of course we get into Neanderthals, sapiens, Devonians, Floresiensis, and so on and so forth. So what exactly happened here climate-wise, and that can be again looked at in the context of this figure. We have looked at in various ways. This is from the International Ocean Drilling Program, which has adopted it from a Nature paper. We looked at the warm Cretaceous, so the time when there was a hot house. So when just before the dinosaurs went extinct with the meteorite crash, CO2 was very high. You can see the global mean surface temperature with respect to 1961 to 1990 baseline was 14-15 degrees higher than present. So obviously that time no Arctic ice, no glaciers anywhere, and lush green forests in the polar circle in the north. Dinosaurs had gone extinct, but we had the Paleocene Eocene thermal maximum there. And we have pointed out that since then there's been this gradual cooling and a drop in CO2 as well, and then came us. We evolved essentially in a very stable climate during the Holocene, and then now the question is where are we headed? So this includes the future projections, which we will not touch here, but I have other courses that you can look at. So here's the Holocene, last glacial maximum coming out, and then the Holocene. So we have already mentioned that one of the hypotheses is that the evolution of Himalayas, evolution of the monsoons, and the accelerated weathering rates because of the mountain building and so on, presumably also the Andes and so on. We'll also invoke the closing of the Isthmus of Panama, which used to be open, that would presumably affect the Atlantic meridional overturning circulation and the climate, but that's still a contested issue as well. So obviously we date the location and the migration of the Indian subcontinent into the Asian plate using magnetic lines. So geolocation is done using magnetic lines. When you're close to the equator, magnetic lines have low angle, and you are far away from the equator, magnetic lines have greater angles, so that can tell you approximately where it would have been at 70 million years ago. And the 70 million number comes from dating rock, finding isotopes that can be used, uranium, etc., to go back that far to date that. So 50 million years ago, it was here crossing the equator, and this is where it is now. Continues to push north into Asia. Himalayas continue to rise, but if you look at the time scales here, we are looking at a north-south section. 45 to 35 million years ago, the pro-Tibetan highland, so by this time 45 to 35, it would have started to push in and create the early Tibetan highlands, and by 23 to 15 million years you already have India, so you can see the collision here and pushing further north here, and 15 million years to 23 million years, you can see the change in topography, and by 8 million years ago you have the Himalayas, Tibetan Plateau, and so on established. Is that related to, let me see, I'm getting a phone call, so probably I'll pause. Sorry about that. To figure out exactly what are the factors that played a role in the evolution of the monsoon itself, was it just the rise of the Himalayas? Was that enough, or did you need additional things? So some modeling exercises have been done. Even now the debate goes on about what is the role of the Tibetan Plateau, for example. Is the heating of the Tibetan Plateau, which is very high, the elevated heating, is that necessary for drawing in the winds and the moisture across the equator to supply the water to the Indian and Asian monsoons, or is that mostly acting as a separation of the cold air and the warm, moist tropical air, and so on? So this paper, I'll just briefly show it, looking at 30 million years to the present, again with the coarse resolution here again. It's looking at the CO2 levels. So CO2 levels were here much higher than today, especially in the last 15 million years. They dropped quite significantly. Of course, there was a longer drop if you go back to 65 million years as well. And sea level changes have happened along with it, and the model considers various periods like the late Oligocene warm period, mid-Miocene climate optimum, and the glaciations. And of course we had time scale changes happening from obliquity, precession to obliquity to ellipticity, time scale variations in the records, but those are also not completely explained in terms of why the time scale change happened. But nonetheless, the model looks at orogeny along the way. So status at 30 million years ago, Drake Passage between South America and Antarctica was open. That would change the glaciation around Antarctica. So opening of the closing of the Drake Passage would have had a very different circulation. Opening created the circumpolar circulation, which isolated Antarctica and favored glaciation. Tasman Sea was fully open, North Atlantic was open, Tibetan Plateau was half of what it is today, and Tethys closes by this model assumption at 15 million years ago, which was the ocean that was connected because of the differences in the rift between Africa and the Middle East, and the opening of the Panama Canal, and so on and so forth. Again, more orogeny here. Panama closes at 5 million years ago in the model. So Tibetan Plateau, linear orogeny occurs during 30 to 25 million years, and 15 to 5 million years from 50% to 100%. So these kind of data are being used to do the modeling. So the conclusion of this paper essentially is that the Indian monsoon had contributions from topography, from orbital forcing, and from what else? Climate change as well. Okay. Right now, we looked at this kind of a figure before. We define global monsoons. So here's the Asian monsoon, which includes the South Asian, East Asian, and West North Pacific monsoon. This is the Indonesian, Australian monsoon, South African and North African monsoons, South American and North American monsoons, and this is the central South Pacific monsoon. So this is basically the ITCZ moving north-south, but these are also all ITCZ related. But the question is, why does the ITCZ migrate so far onto land here compared to elsewhere? Okay, we won't get into that, but the idea is to see along the way what kind of biodiversity changes, vegetation changes happened, considering that the East African coastline is a very critical place for all the fossil evidences and other evidences we have about hominin evolutions, right? So looking here again, 15 millions to about the present, looking in East Africa from 5 south to 15 north, which is a critical region from Turkana into Tana and so on and so forth. So before about let's say 12 million years ago, evidence suggests this was open woodland, and then monsoons began to evolve. So rainfall changed not only over Asia, but East Africa now gets 2 rainy seasons, the short rain and the long rain, during the inter-monsoon periods of the Indian monsoon. So during March, April, May, and during October, November. So lowland rainforests are inferred during those times. Gallery forest, grassland nearby, montane woodland. So you can see the entire latitudinal range changed in vegetation. Wet lowland rainforest, wooded habitats. So it's a mix of vegetations here during the evolution of the monsoon, and presumably because of something like Australia, New Guinea blocking the Indian Pacific pathway and changing El Nino, or other hypotheses that may evolve along the way. Vegetation then slowly transitioned again from 5 south to 15 north into decrease in trees, increase in grass, wooded grassland. You remember Olduvai we talked about before 1.8 million years ago. Wooded grasslands, mostly pollen within 30 kilometers of today. Dryland, open woodland, mesic woodland, grassy plains. Here it's not as dry as before, evergreen brushlands and so on. But basically idea is that this would have given a lot of food, places to hide, and didn't have to go far or fast to find food, whereas once vegetation changed to more open grasslands, savannas, animals had to run faster to avoid predators and to go farther to find food. So that would have favored bipedalism. Remember, most of our great apes walk on all fours, but we walk mostly on 2 legs. So that kind of change presumably was also related to biodiversity change, which itself was related to climate change, which itself was presumably also related to topography change in terms of India, Asia colliding and Himalayas rising. So this kind of biodiversity is still exists. Biodiversity is still around. So this is the areas showing exceptional biodiversity. So we looked at the monsoon regions, and you can see these are all the hotspots. Western Ghats here, Indonesia, Southeast Asia, China, and there are some in Caucasus and these borders of the Mediterranean climate. West African and here Eastern Arc coastal forests of Tanzania, Kenya, Cape Floristic Province, succulent Karoo, and George Philander would tell you that if you go across South Africa here, I think all species of a particular kingdom of vegetation are found here, or some such thing. So you're transitioning from the Indian Ocean side of the climate into the Atlantic side here. So presumably that has a lot of impacts here as well. Okay, so main story is that this is another strong climate connection, biodiversity connection to hominin evolution, which is an interesting piece of the puzzle that fits in many ways, but obviously there are lots of open questions still. I have some wind, but hopefully the recording is fine. Okay.